In our last conversation, we discussed how you can quantify the force between two charges. That's Coulomb's law. And as we worked through that, we also were reminded that you cannot put the signs in the formula itself, but you still had to account for the direction that the charges went. And we did that initially just by saying, well, if they're like charges, they repel. If they're unlike charges, they attract. And that's true. But now we got to work through what happens if there are multiple charges in a given area. And I have to add the forces that are created by those charges. The only way we can add forces is not by using algebraic means, but we're going to add them by the component method. So just a real quick review of the component method. You'll notice that I have a 200 Newton force that's in quadrant 1 and it's at 40 degrees, 100 Newton force in quadrant 2 at 60 degrees, and 150 Newton force in the negative y-axis. Remember, we broke it down into two components, the x component and the y component. And you can do that, of course, you remember we did that just by dropping the perpendicular here and how much y was there to this vector, how much x was there to the vector. And you could add up all of the x's and you could add up all of the y's and all of the x's and then find the hypotenuse of those two legs. That's essentially what we're doing here. So first the sum of the x components. F sub 1x is 200 newtons and it's at 40 degrees and it's positive because it's in the positive x direction. However, f sub 2 is to the left of the y-axis. It's on the negative x-axis, or off of the negative x-axis. So it's negative 100 cosine of 60. And I'm going to say positive, it doesn't really matter, 100 cosine of 90, because remember the x component is asking how much horizontalness is there to this vector. Well, when it's straight down, there's no horizontalness. So I don't really have to worry about is it plus or minus, because one way or the other, it's going to be gone. When you do all the math on that, you end up with 103 newtons. I'm also then going to do the y component because, again, once I add up all my y components and all my x components, I get my, my resultant by using a squared plus b squared equals c squared. So I need my y components to contribute to that. And f sub 1 y is 200 sine of 40. It's positive because it's in the it's going up above the x-axis or on the positive y direction. Plus 100 sine of 60. Again, it's going up, and up is positive y. Minus 150 sine of 90. I'm going in the negative y direction, so it's a negative sign. That all combines to 62.5 newtons. Now I've got my x component and my y component. In other words, I have the two legs. My x leg and my y leg. I have the two legs. I did that backwards, actually. I have my x leg and my y leg this way, and I need to find what my resultant is, my hypotenuse, because they're both positive. That's why I should have drawn it the other way. I'm going to find the hypotenuse, which is then the resultant. You remember that's what we did when we did the addition by the graphical method. This is so much easier, though, and so much more precise. So this is just how I've reconfigured a squared plus b squared equals c squared. This is a squared and b squared equals c squared, but I have to find just r, not r squared, so I take the square root of both sides. I plug the numbers in, and I end up getting 122 newtons. Remember that if you have a negative, we did not in this case, but if you have a component that's negative, you can put it in, but just remember you're also squaring the negative. The negative has to be eliminated because you can't take the square root of a negative number without it being imaginary, and we're not dealing with imaginary numbers in this case. So you end up with 122 newtons. Then to find the angle and the quadrant, we're going to use theta is equal to the inverse tangent of the absolute value of f sub y over f sub x. So remember, it's y on the top, so it's the absolute value of 62.5 over 103, and you take the inverse tangent of that. And guys, I know that I'm going fairly quickly with this. At any time that you need to pause to catch up writing this down, feel free to pause to write this down. I'm only going quickly so that I'm making it as efficient for you as I can, and you only stop for as long as you need to stop. And then I also determined that it was the northeast direction. In your mind, pause for a moment and try to figure out why is it northeast, not northwest, southwest, or southeast. What was the indicator for that? The indicator for that was the fact that I had a positive x component and a positive y component. And the only quadrant where I have both positive x and y has to be the first quadrant, or northeast. So that's my final answer, 122 newtons, 32.3 degrees northeast. So a vector answer has to have magnitude, unit, angle or theta, and direction. All right, now let's talk about how we put this into a electric charge kind of situation. So there's a kind of a how-to for this, and we're going to just talk through that. Excuse me, I'm coming down with a cold. To find the effects of multiple charges, what you're going to do is choose an object of interest. This is super important, that's why I put it in red. Assume it moves while the other charges are stationary. So your charge of interest, and you will always know by the problem which one is the charge of interest, but that charge is the only one that moves. Assume the other two are fixed in place. So what ultimately you're going to be finding is what's going to happen to that charge because of the presence of the other charges. Basically, it's you're identifying one of the charges, the one charge that they're saying, this is the one we're interested in. What happens to this charge because of the other ones? All right, once you've identified that, you're going to draw a force diagram just like we did up here. Whoops, just like we did up here. You're going to draw a force diagram, and the origin is going to be placed over the chosen charge. Then the arrows are going to show the direction, the push or pull for that charge. The other ones, remember, are fixed. So we only care about what's going to happen to that charge because of the presence of the other charges in the field. And then you're going to use Coulomb's law to calculate the magnitude of the forces. Every arrow equals one use of Coulomb's law. You're rooting for fewer arrows because that's just less work, but you can have as many arrows as you want in one of these problems, but every time you have an arrow, then it's going to be a use of Coulomb's law. Now let's pretend that instead of force, these are forces, but let's pretend that these forces were created by the presence of charges. So to find this force, I gave them to you, but to find this force, you would have to do the F sub q is equal to kq1 q2 over r squared. You do the same thing here, and you do the same thing here. As many arrows as there are, that's how many times you have to do the Coulomb's law formula. All right, now let's go ahead and work through this. The last thing you're going to do is you're going to resolve the vectors. You've already got the forces, so now you have to add the forces by the component method. In other words, find your sigma f sub x, find your sigma f sub y, find your r, find your theta, and find your direction. So these are a little bit complicated. They take some more work, they take longer because it's really two separate problems in one. They're Coulomb's law problems, and then they're also adding vector problems. But that's kind of the point of learning how to add vectors, is to put them into a real life situation, which is what you're doing here. All right, so in this case, number 2, diagram the effects of Q on Q1 and Q2 given the following. Now what's interesting about the wording for this is you ought to be able to tell from the wording which ones are stationary and which one is the one that's going to move. And it's actually this right here that tells you that. I want to know the effects on, I have that backwards. I actually worded that backwards. I want to know the effects of Q because of effects on Q. My goodness, I'll get this right. I'm going to blame it on my not feeling well. The effects on Q because of Q1 and Q2. So that might help you to figure it out more. So the one that's moving, the one that's having the effects on it is Q. Q1 and Q2 are stationary. So this was not in the drawing to start with. I just had Q1 and Q2, and Q3 was here. I'm bypassing right now, figuring out the forces because I have no numbers. I just want you to diagram the effects on it. So what's going to happen is these two are fixed. This is the one that moves. So I put my origin over the one that moves. And then I draw the arrows depending on the relationship between the charges in this field. So Q is positive, Q2 is negative. Q is going to be drawn or is going to be pulled towards Q2. So I put my arrow in that direction. Q1 is positive, so is Q2. So Q2 isn't going to go up towards Q1, it's going to be pushed away from Q1. So these are the two forces on Q because of Q2 and because of Q3. I'm sorry, let me say that again. Because of Q2 and because of Q1. That's just how you draw the diagram. Now, I'm going to do a couple other ones for you because this is kind of where students get a little confused with it. So let's say that I have a positive diagram or positive charge here, a negative one here, a negative one here, a positive one here, and we'll just leave it at that. Okay, so what I do is this is my, I'm going to ask what are the effects of this charge, I'll call this Q1, because of Q2, Q3, and Q4. I draw my my axes on here. My origin is right over my charge, that is the charge of interest, and I'm just going to go around and figure out what's going to happen. So Q1 is going to be pulled towards Q2, it's going to be pulled towards Q3, and it's going to be pulled away from, so there's going to be double force in this direction, away from Q4. Let's try another one. Let's say that I have Q1 here and it's positive, and Q2 is here and Q3 is here, and we'll make that one positive. And I want to know what's going to happen to Q1 because of Q2 and Q3. I put my axes over the one that I care about, and then I just work out what are the forces. Is it going to go towards it? Is it going to go away from it? They're unlike charges, so it's going to go towards it. And maybe that's a better way to ask it. Is it going to go toward or away? These are like charges, so they're going to repel. It's going to move in the opposite direction of that charge, so it's going to go that way. And this is what my force diagram would look like. Okay, we're going to do one of these where we actually figure it out from the beginning. So the first thing I have to do is, and I've kind of put all of this here together so you can see it all at once and you can kind of look ahead to why I'm doing some of this stuff. So the question would be, this is Q1. This one is, I did not label these, I'm sorry. Oh, this is Q3. I apologize for that. I did not finish my diagram. And that's Q2. All right, so I have Q1, Q2, and Q3. And I want to know what are the effects on Q1 because of the presence of Q2 and Q3. First thing I need to do is find out what all the forces are going to be because of that. So I need to know what's the force between these two charges, which is what I did over here. The force of 2 on 1. You could have 1 on 2, I don't really care, but it's I'm actually worried about what are the effects on 1. So it's a good way of writing it. So I put it into my Coulomb's law equation, and notice that Q2 does not have a negative to it, and the answer is 0.0185 newtons. And I don't need to worry about direction because that's not going to be the ultimate direction anyway. Then I worry about what is the effect of this charge on this charge. And I fill in the equation just like you're supposed to. And both of them are positive, so I didn't need to worry about not including the negative in that one. And I ended up with 0.135 newtons. All right, so now I'm going to do my force diagram. So here's my positive charge. That is the charge of interest. So I've got my axes going through it. And I'm going to ask myself, what is going to happen to a positive charge in the presence of a negative charge? It's going to move towards it. And so that's why I have that arrow, because they're all on the y-axis. It's just going to go straight down. And then I ask myself, what's going to happen to Q1 because of the presence of a positive charge? They are like charges, and so they're going to repel. So Q1 is not going to be drawn toward Q3. Q1 is going to move away from Q3. And so that's why I have the arrow drawn in that direction. I put next to them exactly what I found the forces to be. So this force is 0.0185, and I'm renaming it 1 just because it's easier to do those designations in these formulas. And this force is 0.0135, and I'm naming it F sub 2 for these equations. Now I just break it down into my components. F sub 1x would be, this is my F sub 1, so F sub 1x would be 0.0185 cosine of 90. But again, remember that cosine of 90 is asking for how much horizontalness is there in a perfectly vertical line. Cosine is horizontal. Remember, it's sine y, sine y. So sine is the vertical, cosine is the horizontal. There's no horizontal piece in a perfectly vertical line, and so that's a non-starter. Just dump that one. Minus, and it's negative because it's going in the negative x direction. Always ask yourself, what direction is this vector going according to the y-axis? Is it to the right of the y-axis? It's positive. If it's to the left of the y-axis, it's negative. So that's why that's negative 0.0135. I do include the negatives here. I don't include them here. Remember, we've always done negatives when we're finding vectors. So there's a distinction. No negatives in my Coulomb's law, but always negatives when you're resolving vectors. And then I end up with a negative 0.0135 newtons. And sigma f sub y, same thing. This is a perfectly horizontal line when I'm looking at the vertical piece to it, so that's gone. And this is negative because it's going down. So my final answer is a negative 0.0185 newtons. So I found my x and my y component. I found my two legs of the right triangle. So now I have to find the hypotenuse by using a squared plus b squared equals c squared. I plug that into the equation. I did not bother putting the negatives in because I know they have to disappear. If you put them in because you're just a formalist and you've got to do everything with your I's dotted and your T's crossed, God bless you. I love that if that's true. I just don't want any student to get confused that by putting it in there, then they don't necessarily square it as well. So when I do that whole thing, I end up with 0.0225 newtons. Then I have to find my angle. My angle is going to be the inverse tangent of the absolute value of sigma f sub y over sigma f sub x. I just plug my y number in on the top, my x number in on the bottom, and I can go ahead and include my negative because the absolute value is going to take them out anyway. So I have an angle of 53.1 degrees. But now I have to figure out what my direction is going to be. And because I have a negative x and a negative y, the only quadrant where both x and y are negative is quadrant 3, which we call southwest. So my final answer is, again, I have to have magnitude, unit, angle, and direction. 0.0225 newtons, 53.1 degrees, southwest. All right, now your homework for this is going to be, give me a second here, I have the wrong one. I'll tell you what, I will just post it on PowerSchool so you can see right before the video what the homework is going to be, which is probably better for you because I think I may kind of narrow it down from what I originally thought. It is a lot of work, these problems are, and I want you to be good at them, but I don't want to burden you unnecessarily with problems that then you're just doing because they were assigned, not because you still need to practice the process. So I'll give that some thought. When you get into them, if you just start getting confused about where your arrows go, how you reflect on what is the charge of interest and what happens to that charge of interest, if you struggle with that, let me know. We can work through a couple more of those together to kind of get you on solid footing. But otherwise, it's just following the process. You've done Coulomb's law. You know how to do it. It's straightforward. You've done adding vectors by the component method. You've done that a lot of times, so now you just work through the process and follow the step by step. Find sigma f sub x, find sigma f sub y, find r, find theta, and smooth sailing. Just a lot of work, but smooth sailing. Let me know if you need me for anything though.